Welcome to the second half of Algebra 3A, Relations and Functions. We're now going to look at some types of functions and some properties of functions. The first thing we're going to look at is discrete functions versus continuous functions. A discrete function is made of points that are not connected. Okay, often this means there are not in-between values. So if you are charting how many siblings do you have, no one has 2.5 siblings, so you would just have some specific values that might be plotted as points, but you're not connecting in between. So you can have a lot of different types of discrete functions, but they're made up of these disconnected points. And then we can also have a continuous function. This forms a graph that is a line or smooth curve. Okay, so we might have something that looks like this. It is continuous. Between any 2 points, all the values in between exist as well. So that would be a continuous function. We also have some particular properties or values on a graph. The first that we're going to look at are the x and y intercepts. The first is the x-axis, which is the x-coordinate. The first is the x-intercept, which is the x-coordinate. Where the graph, that's the function that we're drawing, crosses the x-axis. Okay, so if I drew a graph like this, then this graph crosses the x-axis. Here's my x-axis. At this point, let's say that's -5. The x-coordinate where this crosses the x-axis, -5, and the y value there is at 0, is the x-intercept. Then similarly, we have the y-intercept, which is the y-coordinate. Where the graph crosses the y-axis. Okay, so looking at this graph, that's the function that we are drawing, appears to cross the y-axis, the vertical axis, at the point 2. So the x value there is 0, and the y value is 2. 2 is the y-intercept. Now, when we write these for this class, we're always going to write it in the coordinate point form. So we're going to give both the x and y values, but the y-intercept is going to be where the graph crosses the y-axis, and the x-intercept is going to be where the graph crosses the x-axis. So that's the x-intercept. Our next idea is end behavior. And end behavior is simply how the values of the function behave at the ends of the graph. How the values of a function behave at the end of each graph. At the end of each graph. So when we talk about the end, we're talking about the far left and the far right. Okay? If I were to draw, for instance, this function, and I want to know, is my graph rising to the left and to the right, or is it falling to the left and to the right? In this case, to the left, or as x approaches negative infinity, my graph is pointing somewhat down, which means it is falling, or we say it falls to the left. Whereas to the right, since my arrow is pointing upwards-ish, I would say it is rising. It rises to the right. Same thing here, end behaviors, what's happening at the very end. Even if my graph did a bunch of this in the middle, woo, 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 and even if it kind of flattened off a little bit here and kind of flattened off a little bit here, my end behavior says I don't care what's going on in the middle. That has nothing to do with end behavior. End behavior is what's going on at the very end. And here, even though my arrow is mostly pointing left, end behavior is always up or down, rises or falls. In this case, it is rising. And in this case, it's rising slowly, but it's also rising. So it rises. Okay, that's end behavior. It's just what's going on at the very outside. Next, we have line symmetry. Line symmetry is just when a function is divided by a vertical line, so this vertical line divides the function into two halves that match exactly. Two halves that match exactly. Okay, if I wanted to draw a line with line symmetry, first I want to know, where is my vertical line, that vertical line that it's splits it in half. So maybe this will be my vertical line. Okay, and then if my graph did something like, okay, -4, and then goes up through here, and then maybe comes out like this. Okay, if I want this function to have line symmetry, then I need it to match on the other side exactly. Now, by hand, I'm not going to get this perfect, but that would have line symmetry. If I took this side and put a mirror down as this vertical line, the other side matches it exactly. So this has line symmetry. Another function that might have line symmetry is maybe if we'll do something a little bit fancy here. If I do this and go through here and then go like that. Okay, this line cuts this function into two halves that match each other. It has line symmetry. So that has line symmetry. A typical linear function does not have line symmetry because there's no line that I could draw that would make the right side exactly match the left side. So this does not have line symmetry. Or if I had something that looked like this, the right side, if I were to flip it over, does not exactly match the left side. This does not have line symmetry. We have three more major ideas here. First is extrema. These are the minimum and maximum values. The min, just going to say min, and max y values, or range y values. Okay, you could think of these as hills and valleys. If I draw a graph like this, then I'm going to have some maximums here, and we call this a local maximum. We have a little local maximum here. And I have some minimums here. That's a little local minimum. If this went down, minimum. Then I'll have a global maximum up here. This becomes the highest possible area. And a global minimum. This is the lowest possible area. These are little hilltops and valley bottoms. So those are our extrema, minimum and maximum y values. Then each point on a graph is either positive, negative, or neither. Positive is when the graph is above the x-axis. It's where the graph is above the x-axis. Always the x-axis, the horizontal axis. Negative is when the graph is below the x-axis. So everything here above the x-axis, anytime the graph is above the x-axis, it's going to be positive. Okay, so all of this is positive, and all of this is positive. And any place that the graph is below the x-axis, then it's negative. So it's negative all here and through here. Positive, negative. Okay, and then whenever the graph is on the x-axis, it's not above or below, it's on, that's neither. Right, and then finally, we'll also have places where our graph is increasing, okay, and decreasing. And we determine increasing and decreasing always reading, think of it as like reading from left to right. If I'm reading from left to right, when the graph goes up, it's increasing. Graph goes up. Or if the graph goes down, then it's decreasing. We're going to add one here. It's constant. Constant if the graph stays the same or flat. Stays the same or is flat. So if I drew a function that looked like this, okay, then it's increasing. I always start from left to right. It's increasing, going up, going up, going up. I'm climbing uphill, 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 and I stop. Okay, so it's not flat, it's round here, it's never quite flat, but now, oh, I'm at the, going on the downhill part of the roller coaster, down, 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 down. Okay, so that's decreasing. Increasing, green, increasing, decreasing. Then this section right here is flat, so that's constant. The graph isn't going up or down, so it's constant. And then we have a little bit more going up again, so that's increasing again. Okay, so those are a lot of different parts of graphs. Don't sweat if you don't have it all down right now. We're going to play with these, we're going to work with these, we're going to draw our own graphs, and then we're going to be able to see how can these represent things from life. So make sure you have all of these written down with some little visual examples to help you remember, and I will see you in class. Bye.